Okay, here we are in section 8.3. Here's where we start the application to derivatives. And we are going to spend several days here. There's going to be at least one or maybe two group quizzes on this type of problem. These are called max-min problems. So we just spent a couple days identifying critical points, and when those critical points are max and mins. Now I've got story problems to match, and it's really a 5-step process. And you need to do all the steps. First thing you want is to sketch and label a picture. Then you want to write an equation for what is to be maximized or minimized. And this could be maxed or minned. I don't know if I spelled that right or not. I don't even know if they're words. But anyway, this could be maximize the area, maximize the perimeter, minimize the volume. So lots of formulas. You might have to Google some of them for different shapes if you don't remember them, but I'm sure if you just did a quick search, you can find the formulas that you need. Most of them are simple and rectangular stuff, so not too worried about that. So write an equation for what is to be maximized or minimized. Then write that equation with one variable. And you're going to do that by using a second equation. And you'll understand that when we actually get into one. Okay, after you've done that, this fourth step says you have to identify a reasonable domain. You don't always have to do this. You can kind of hold off on this if you want to until the end, because when we find a critical point, remember it's where the derivative equals 0, and say you want to maximize something, but your critical point comes out to be the minimum, then your answer is actually one of the endpoints on the domain. So you don't have to write the domain unless your max or min comes out opposite of what you want at the end. But again, don't worry about this yet until we go through it. So identify a reasonable domain. Because here you would use one of the endpoints. All right. No. Okay. Then use derivatives. To find x equals c, the critical point. Remember, when the derivative equals 0, we've got a critical point. It's either a max or a min. And what we're going to do to check to see which one it is, instead of doing the before and after, there's a little shortcut. So if the derivative equals 0, and then if the second derivative at that point is positive, that means the graph is concave up, which would have made the c be a minimum, because it's at the bottom, because it's concave up. If the derivative equals 0, and then the second derivative is negative, that means it was concave down, which means now we've got a maximum. So you'll be able to identify your critical point just by doing the second derivative test. So if the second derivative is positive on that critical point, it's a minimum. If the second derivative is negative, then it was a maximum because it's concave down. Okay, and then answer the question. So I'm going to go through a couple of story problems with you so you get the feel for them. Like I said, we're going to be spending several days here in this section and having a group quiz or two with this style problem. Alright, first one. I'm going to do a new page. Okay, your job is to help out a farmer. The farmer has 1,000 feet of fencing. And he wants to build a rectangular corral with one edge of the rectangle along a river that's not going to need any fencing. So we want a rectangular corral along a river. And the goal of this corral is to have the maximum amount of area contained. So we want to maximize the area of the corral. What dimensions should he build the corral? Okay, so we've got our river flowing through here. There's my river. Draw a picture. I'm at the first step here. Draw a picture. So we've got a rectangular corral. With those three sides are where the fencing is going to use up. So we know that the sum of those three sides is going to be 1,000 feet. But my goal is to maximize the area. So I've got my picture, but I don't have any labels. I don't know what the dimensions are, and I've got two different dimensions here, length and width. So I'll call one of them X and one of them Y. So now the picture's done. I want to maximize area, so I want to write an area equation. Well, the area of a rectangle, shouldn't have to Google that one, X times Y. Now I'm at the step where it says, write that equation with one variable in it. You may have to use a second equation. Not always, but in this case we are, because I've got an X and a Y in my equation. So when I said use a second equation, well, you have to look back for another piece of information that will allow you to write an equation. And if you look, I've got 1,000 feet of fencing. Well, that means I can write a perimeter equation. The perimeter of this three-sided rectangle is 2x plus y. And I know that that perimeter has to use up all 1,000 feet of fencing. So now what I can do is either solve this for x or solve this for y so that I can substitute back over here. And if I look, it's going to be, I think, easiest for me to just solve for y by subtracting the 2x from both sides. So I've got y equals 1,000 minus 2x. So now I can take that, substitute it in for the y, and now rewrite my area equation so that it only has one variable in it. So it's x now times the quantity 1,000 minus 2x. Okay, so I've got the equation with one variable. Now it says identify a reasonable domain. You might have to use one of the endpoints at the end for an answer, so don't worry about that yet, but identify a reasonable domain. Well, because I've got this equation in terms of x, I want a domain for x. Again, this step isn't necessary unless my answer comes out opposite of what I'm looking for. But we'll just say, if I think about x for a range of values, x is the dimension along here. Well, I know I have to use some of the fencing, so I know it's got to be greater than 0. Just common sense. And if I've only got 1,000 feet of fencing, I know that, what do you think x would have to stay under? Just common sense. I've got 1,000 feet of fencing here. I can't use all of it on these two sides, so it'd have to stay under 500 feet. Because if it equaled 500 feet, I'd use up all 1,000 there, and I wouldn't be able to create a rectangle here. So I've got to stay under 500 feet for that dimension. So that was just kind of common sense for my domain. All right. Again, that might not be needed at the end. In this one, it's not going to be. Okay, now we do derivative. Now I'm looking for the critical point for this equation. I want this area to be maximized. So if I do the derivative, set it equal to 0, that's going to tell me where critical points are happening on this equation. But before I do that, I think I want to distribute my x so that I don't have to do a product rule. So 1000x minus 2x squared. And now I'm ready for derivative. So derivative here is 1000 minus 4x. I want to set that equal to 0. That will give me a critical point. Solving for x, I'm going to subtract 1000. Divide by the negative 4. And that'll give me positive 250. So I know there's a critical point at 250. I just don't know whether it's a maximum or a minimum. So I'm going to do that second derivative test at 250 to see whether I've got a max or a min. So I'm going to do second derivative equation. And if there's still a letter left, I'm going to plug in 250. So second derivative here, derivative of 1000 is 0. Derivative here is a negative 4. So I don't have to plug in the 250. The derivative is, second derivative is negative, which makes this concave down, which makes my critical point a max, and that is what I wanted. If this had come out a min, then either one of these, I'd have to check to see one of these would have been my maximum. But I got it off the bat, so I don't have to worry about my domain. Okay, so now I got to answer the question. The question said, what are the dimensions for my rectangular corral for the farmer? Well, I know the x is 250. I can substitute back into right here to get the y. So I'll substitute in 1000 minus 2 times 250 equals the y. That's going to give me 1,000. So 1000 minus 500. I got 500. So I've got a 500 foot by 250 foot rectangular corral that will maximize the area with that constant fencing there of 1,000 feet. Okay, let's do another one. We're actually going to set up 2 more with you. You're going to finish them in your homework. Number 2 happens to be part A of number 2 in your book. It's a motel problem. You're going to have a 6-room motel. Each room is going to have 350 square feet in it. And we want to, it says, what dimensions should the rooms be in order to have the minimum total wall length? So find room dimensions to minimize wall length, total wall length. So we want to minimize the materials it takes to build the room, but keep this area the same, to minimize wall length. And the book does give you a picture. The hotel is going to look like this. A little strip motel with 6 rooms in it. All the same size. 1, 2, 3, 4, 5, 6 rooms. Each room is going to have 350 square feet. Okay, now I got to get my dimensions, and my goal is to find the dimensions of a room. So I'm just going to go with my x by y. So now write an equation for what is